Okay, we're into Unit 7. Unit 7 is acid-bases and acid-base equilibrium. Go ahead and read the learning objectives. This is a very intense unit. It brings together equilibrium, which you learned in Unit 4, into how equilibrium works in acid-base chemistry. Let's go ahead and define acids and bases based on two models. One is the Arrhenius model and the other one is the Bronsted-Lowry model. In the Arrhenius model, an acid is one that ionizes to produce hydrogen ions. The Arrhenius base is one that ionizes to produce hydroxide ions. Here we have an example of an Arrhenius acid, right here, acetic acid. When it's in water, is going to be in equilibrium and it ionizes into acetate and hydrogen ion. You're going, what happened to the water? Well, really that hydrogen ion is going to attach to the water molecule. And when that happens, it's going to create what is called hydronium ions. So you can actually represent either or. It's easier to represent as hydrogen ion, but they're really representing the same thing, which is the hydrogen ion concentration. So if again you see water right here, water looks like this, H2O, but then the hydrogen ion attaches to the oxygen, creating this hydronium ion that you see here. An Arrhenius base is where a substance produces hydroxide ion, and that's what you're seeing in this reaction with water. It's just ammonia ionized in water to form ammonium and hydroxide. But the hydroxide is what really makes this an Arrhenius base, whereas hydrogen ion or hydronium ion is what makes this an acid, Arrhenius acid. Now we go to the definition of a Bronsted-Lowry acid base. Bronsted-Lowry, also abbreviated BL, I call this the BL acid, is capable of donating a hydrogen ion. So there's an action here. There's a donation of a hydrogen ion, a proton. By the way, just imagine a hydrogen ion or a hydrogen atom without an electron. That means it's a proton. That's why this word proton is interchangeable with, or it represents a hydrogen ion. Now we get to Bronsted-Lowry base. It's capable of accepting a hydrogen ion. And usually when we have such a situation, it's actually BL model. You're looking at it in conjugate acid-base pairing that occurs in an equilibrium reaction. So here I have I'm going to define what's happening. So I see here that between the reactants and the products, and this reaction is this reaction up here. So think about this, but it's another model for defining what an acid base is. In this situation, you actually have a pairing going on, a pairing on the reactant side and a pairing on the product side. When you look at this reactant and compare it to the products, what you're going to notice is the ammonia gained a hydrogen from the water. So a proton was donated to this substance called ammonia. So from the water to ammonia. So that means since this substance donated a hydrogen ion, it's an acid. So water acts as an acid. Now, since ammonia accepted a hydrogen ion or a proton, it's a base. Now we go to the products. On the product side is the conjugate of that. And so here we have an exchange where we're looking, since this reaction reverses itself, now we can go this way. And so we're looking for what happens from here to here. And it looks like ammonium became ammonia by losing a hydrogen ion. And that's why you're seeing the hydrogen ion transfer over to hydroxide to make water. And we can do this again because of the equilibrium. The reaction reverses itself. And when this happens, again, by definition, this is an acid because ammonium transferred a proton to hydroxide ion, as you see here. That means the hydroxide ion is the base because hydroxide ion accepted a proton. Now, it's hard to see it like this, where you're seeing acid base on both sides. So when I say acid, how do you know if it's this substance or this substance? So we're going to delineate this side by calling it conjugates. So this is a conjugate acid and this is a conjugate base. I like to think of this. Every base is linked to its conjugate acid. So this base becomes its conjugate acid. This acid becomes its conjugate base, and they look very similar to one another. The conjugate means if you're a conjugate, you're similar to that each other. Now let's look at B. So once again, I look at the reactant, I look at the product, it's in equilibrium. So I compare the reactants and products. I see that F here, or HF here, became F minus. So here's the conjugate of HF here. So it looks like HF donated a hydrogen ion. Who did it donate it to? Well, it must be this partner here. Water accepted a hydrogen ion to become hydronium ion that you see here. So here's the conjugate for water here. A hydronium ion is water's conjugate. So let's go ahead and identify. And before I identify, I'm going to actually put the arrows to show for how the proton is being transferred. So it looks like H plus is being transferred from the HF to the water. And then if I go backwards and look at the products, it looks like the hydronium ion is going to transfer hydrogen ion to the F minus. So once again, who's the acid? The acid is the one donating a hydrogen ion. So this is the acid. Base is the one accepting a hydrogen ion. I'm always looking at the definition to help me to define the scenario. Now I go to the product side. This looks like hydronium, looks like it donated a hydrogen ion. F minus accepted a hydrogen ion. Once again, since it's the products, we call it the conjugates. So that's how we determine the Bl acid-base conjugates. Now, conjugate acid-base pairs are very important, so practice this skill. Make sure you really do. If you need more practice, you go on the internet and just go and find some more conjugate acid-base pairs. Just type that in. I'm sure you'll find that. Some key ideas with the conjugate, especially as we get into titrations. The stronger the acid, the weaker its conjugate base. Okay. So if the substance is a strong acid, that means it dissociates more and more. That means the base doesn't want to, its conjugate base doesn't want to accept a hydrogen ion because it's a stronger acid. It would rather be dissociated than to accept a hydrogen ion. Which means the weaker the acid, the stronger its conjugate base. So weaker acids actually don't ionize very easily, and so they easily their conjugate base accepts a hydrogen ion readily, which means it's a stronger conjugate base. Recall, weaker acids do not ionize more molecular species present than the ions that make up that substance. So here's your whole molecular species. It's neutral usually. The ions that make the substance are the cation and the anion of the acid. The stronger the base, the weaker its conjugate acid. Same idea. The stronger means it dissociates much more, and that means its conjugate acid has a harder time. Its conjugate acid has a harder time donating a hydrogen. And so the weaker the base, the stronger its conjugate acid, meaning the weaker the base means the substance doesn't ionize as easily, so that means the conjugate acid. Um, my apologies. It's supposed to say conjugate acid. So it has a stronger conjugate acid. Yours should be edited by now. So this should be the word acid. Stronger the base, the weaker is conjugate acid, and the weaker the base, the stronger its conjugate acid. Perfect. Weaker base do not ionize so much, do not ionize much, so more neutral species be present than the ions that make up B in water, of course. That's where the hydroxide ion comes from. The equilibrium reaction will often be written in the direction favoring the ionization of the stronger acid and the stronger base. So let's take a look at these examples. In this pair of examples, you have hydrofluoric acid and its conjugate base, and then hydrochloric acid and its conjugate base as well. So to figure out which conjugate base is stronger, what you do is you look at the acid of that conjugate base. So here's your acids, and the one that is stronger is going to yield a weaker conjugate base. The one that's weaker will have a stronger conjugate base. So here I have the values written down from the next page, the Ka values for each of the acids that I see in both these two pairings. For this first one, I'm comparing the Ka value of these two acids, the acetic acid as well as the carbonic acid. And I see that the stronger acid is going to be the one with a higher Ka. Higher Ka means the acid strength is higher, stronger, because it ionizes more. The substance will form more products, which means, and just reminding you, going back to what K represents, it's a ratio of products over reactants. If there's more products, that means the Ka is going to be greater, which means, and the products in this case is the ions that make up these two, or this acid. So that means the acid strength increases if the Ka is greater. Between the two acids, carbonic acid and acetic acid, the value that's higher is this value right here. So that means acetic acid is stronger. That means the stronger acid is acetic acid. Which one's the stronger base? If acetic acid is the stronger acid, that means that the weaker acid is carbonic acid, and its conjugate base is going to be stronger. So its conjugate base in this case is, the base in this case is not conjugate, but the base is going to be hydrogen carbonate, which is going to be stronger. Now, the same thing goes here. I'm going to identify who's the acid, who's the base. Here's my acid, here's my base, here's my conjugate acid, and here's my conjugate base. After I identify that, then I look at my Ka values to see who is higher, and it looks like hydrofluoric acid is higher. So I'm going to star that. That means hydrofluoric acid is a stronger acid. The weaker acid is methylamine ammonium, which is this guy here, or CH3NH3 plus. That means its conjugate, or sorry, its pair in this case is going to be a stronger base because it comes from a weaker acid. And that means I'm going to write in CH3NH2 is my stronger base. So this is the chart that I looked up earlier to figure out who was a stronger acid or a stronger base in the end. This is written actually as the Ka values. I can easily interpret this in the Kb values by just taking Kw divided by Ka. That's how you find Kb, is you take Kw divided by Ka. That will be the Kb values for all of these as well. But this chart is put in that format, so I'm going to look at it in that format. This is actually from high to low Ka values. So the strength is, the acid strength is decreasing going downward because the values are decreasing, Ka values. In other words, the acid strength is increasing going upwards. These are all the acids and its conjugate base. So these are the conjugates for each of these acids and the names of them as well. But this chart, you oftentimes are given your K values, whether it's Ka or Kb ultimately in the end. Your first homework is a worksheet, and it's really practicing understanding your acids and base based on the Arrhenius as well as the Bronsted-Lowry model. Mostly the Bronsted-Lowry model, because that is going to be really an important part of all the acid-base chemistry. You're going to see a lot of that particular model for defining acids and bases. Let's do some basic calculations of pH, pOH, and of course the hydrogen or hydronium ion, which is of and which the same, and then hydroxide ion. Okay, we know some basic ideas. pH less than 7 is acidic, greater than 7 is neutral, basic, and then equal 7 is neutral. pH and pOH always add up to 14, so if pH is less than 7, that means pOH must be greater than 7 proportionally, and vice versa. So you're always going to see greater than 7 means pOH is going to be less than 7. And of course, equal 7, this must be equal 7. That's why they add up to 14. This is a great map to tell you what equation to use whenever you're going through one calculation or another. Understand that the word p means this right here. It's the negative log of anything. So you can do p of anything, and that way, or that anything is just taking the negative log of that value. These equations help us to either go forward or reverse in our calculations, knowing what the p is based if I need to inverse it, okay? Ka times Kb always equals Kw, as you see up here. This equation actually comes from that very idea, and these can be derived easily from one another. And you're going to see me derive some of these equations along the way. Of course, understanding the function of what P represents, which is negative log. So let's go ahead and practice in example 4 and 5 with that pH map that we saw earlier. Let me just go over a quick little function of log. So if I take the log base 10 to some power of x, that would equal x. So it's basically an exponential function, and we get it. We can easily solve for our value from the exponent of what it is, okay? So when you take the negative pH, which is negative log, which is your pH, you can easily find your values without a calculator, as long as your number in your scientific notated number has a 1 in it. Because the log of 1 is 0, and that's why you can zero this part out easily. And that's what you're seeing with the no calculators, is most of the time that scientific notated number has a 1 to zero out that part. And all you have to do is just find the exponent of this concentration. So this is the concentration of OH, and the exponent is -9. So when you take the negative log of that 10 to the -9th, you get 9. And that's precisely what we'll put into the pH, or sorry, POH. Class sig fig. The rules for significant figures with respect to log is you add one more sig fig. So if this is one sig fig already, you add one more sig fig, that would give you 2. So log functions, it has its own sig fig rule, and that's why this number is 9.0. pH and POH always adds up to 14, so this must be 5.0, because pH plus POH always equals 14. And you'll notice that the POH is greater than the pH. And just from the pH alone, I like to use pH because I'm more familiar with the pH. Anything less than 7 means it's acidic, and so you can see that to be the case. But you also can see it in the concentration, and we'll talk about that once we fill out the concentrations of both the hydroxide ion and the hydrogen ion. I know that when I multiply these two values, it's going to give me 1 times 10 to the -14th. But I don't even need to do that. I know that this is going to be 1 times 10 to the -5th. Just like my exponent 5 right here. Which concentration is greater? You can tell that it is going to be the 1 times 10 to the -5th, which means you have more acid. More acid than base. More acid than base makes the solution acidic. So you can look at the pH to determine this acidity, or POH, but I'm much more familiar with the pH scale. But you also can see in the concentration, there's more acid than base, thus it's going to be more acidic. All right, this is all without a calculator, so please work your way through. I'll do a couple more. If the POH is 2.0, I know my pH is going to be 12.0. It looks like my pH is greater than, and it looks like it's basic. If I go directly from the pH, using that to determine my acidity and basicity of my solution, or neutrality. Hydroxide ion is going to be 1 times 10 to whatever that exponent power to the negative of that exponent power, which is 2. So it's going to be -2. My hydrogen ion is 1 times 10 to the -12th. So it looks like there's more hydroxide ion than there is hydrogen ion, so it's more basic. So this is quite easy for the most part when it comes to no calculator. And the goal is to not be able to have to use a calculator for these concentrations, or pH and POH, if it comes to it in the multiple choice section of any AP exam. So equals would be 14. That means it's neutral. The solution is neutral. And 1 times 10 to the -7th. 1 times 10 to the -7th. And they're equal here as well. All right, you should pause and work through the calculations for the rest. So now you are in example 5, you're going to use a calculator for all of these, which means pull it out and make sure you really use the map and know how to go about using them, doing the calculations with a calculator and the map, okay? So I know, this is what I know, that multiplying this one times this is going to be 1 times 10 to the -14. So in order to figure out the hydroxide ion concentration, I just take 1 times 10 to the -14 divided by this number. And I'm going to work that in my calculator. So the next step is to now define what P is, which is negative log of the concentration of hydrogen ion. So pH is negative log of this value. And then POH is negative log of this value, and I'll do it for each. I also could have opted to do the the pH and then take 14 minus that to get the POH also. So those are your two options. And I'll take the 14 minus because it's faster, 9.37. Looks like my pH is less than 7, which means it's acidic. I can see it also in the concentration, that the concentration of the acid is greater than the concentration of the hydroxide ion. And pOH is greater. So go ahead and work through these problems. You're just going through it using that map. For this next one, I am going to, since I'm given pOH, I know that pH and pOH adds up to 14, so I'm going to subtract 3.5 from 14. In doing that, I get 10.5. And then I can see that it's basic as far as the solution right off the bat. Then I can take, now to reverse this, in other words, if you're given pOH here, to find the H plus concentration is just to take the 10 to the negative pOH. So whatever pOH is, take the negative of that, and then take 10 to that. Now 10 is actually, that inverse function is actually on the log button. So if you second log your calculator, you'll see 10 to some power. And you just take it negative 3.5, and you should get the concentration of OH. It ends up being 3.16 times 10 to the negative 4. I know I could also do the same thing here where I'm taking 10 to the negative pH, and I'll do that. Or I could also take 1 times 10 to the negative 14 and divide it by the OH concentration. So I have two options, two routes to get to the same result. In this case, the result is 3.16 times 10 to the negative 11th. So that's a concentration of H+. The concentration of hydroxide is greater than the concentration of hydrogen. Go ahead and pause the video and solve the rest. And when you unpause, you'll see the answer. So here's the answer, the rest of the answers for example 5. Let's go into modeling acids and bases based on their strength and talk about percent ionization. If you look at this substance here, hydrochloric acid, it's in water, so that's why you see water added here. I'm going to dissociate that acid in water. When I do that, I'm going to see that this hydrogen ion and this chloride ion are completely dissociated. Now I could also represent water in there, and when water is in there, now it's hydronium ion. But it is easier to be represented without the water, so I'm going to represent it as hydrogen ion. You can interchangeably use either or. For this strong base right here, sodium hydroxide is a strong base. This strong base, when it goes into water, is going to ionize and dissociate completely into hydrogen ion and hydroxide ion. And the reaction for this is NaOH is going to dissociate into Na plus and OH minus. And notice this reaction is strong, so it's one direction. Doesn't go back the other way like a weak acid or a weak base would do. Likewise, this strong acid, when you write the reaction, is going to look like this, HCl, and it's going to completely ionize all of it. So you're going to form H3O plus and F minus. If you want to write it without the water, you just would say HCl, forming H plus ions and F minus. I really would prefer to write it this way because it's got no water to distract me. So that's why. But if written this way, you actually see the Bronsted-Lowry acid and base and its conjugate going on. So this actually follows the Bronsted-Lowry model pretty nicely. You do need to know your strong acids. Now, AP doesn't include this particular one as a strong acid, but it is a strong acid. You should know all your alkali metals with hydroxide ions as well as alkaline earth metals are strong acid. But you should know that these two have limited solubility, so that means they don't dissolve very easily, and that's why they're not as strong as the other ones, okay? Just like molar solubility, acids have a percent ionization. And all it is the amount that is ionized over the original concentration that you have of the acid, the whole acid, the molecular species, times it by 100. So this tells you how much ionized of the acid compared to its original concentration. Now we get into a weak acid scenario. In a weak acid scenario, you see most of these substances stay together. And then maybe one or two or one ionizes into hydrogen ion and F minus ions. So you actually see them separated as ions here. Now in this case, ammonia, or let's write the reaction. So HF, based on the Bronsted-Lowry model, is going to ionize to form H3O plus and F minus. Practice writing these reactions. And once again, it's easier to see it with hydrogen and no water. So it's just hydrogen ion and fluoride ion without, not as the Bronsted-Lowry model. Now we go to ammonia. In this scenario right here, ammonia is going to need water. So you're actually going to need to see water in this reaction so you can see how ammonia accepts a hydrogen ion. Upon accepting a hydrogen ion from water, you're left with water expelling as a hydroxide ion. So those are your two ions that make ammonia. Now once again, it's a weak base, so you're going to see a lot of ammonia molecules, not ammonium, because this substance doesn't ionize readily. So you're going to see more of the ammonia as a whole species than the ions that make up that substance. When I write the reaction out, it's NH3 ionizing with hydrogen transferring over. And once again, you can also show the hydrogen transferring over here as well. In the Bronsted-Lowry model. And then when that happens, you form ammonium ion and hydroxide ion. Okay. There's no other way to write a base reaction other than what you see here. Now, because this is a weak acid scenario, and there's an equilibrium, we actually can figure out and understand the equilibrium pretty nicely with our understanding of equilibrium. It's always products over reactants, and we call this the Ka for acid. And so when we ice this, as we normally ice an equilibrium reaction, but now look at the change over here for the acid. The amount of change is how much ionizes, forming equal molars, because it's stoichiometrically the same, 1 to 1 to 1, of your two ions that make up your acid. And then, of course, equilibrium is simply just adding these two columns or rows together. And then you substitute to your Ka, which is a ratio that is constant at a certain temperature. And you can actually figure out what the equilibrium amounts of your acid are based on that, as long as you have your Ka. Now you should always do if you're going to assume X is small, like you did here, Since X is much smaller than the original concentration of the acid, then you can actually just get rid of the X, and so the concentration of HA originally is what you see. You zero out the X, and so the original concentration is what you see here. But you do have to validate that assumption by doing the percent ionization. So you have to take the X right here and divide it by the total original concentration and times it by 100 to find if it follows the less than 5% rule for what a weak acid is. So only less than 5% of the weak acid ionizes. Okay, so once you get to a base, the weak base is going to ionize in water. And you have to have water here because as bases, according to Bronsted-Lowry bases, they accept a hydrogen ion. And where it's going to accept a hydrogen ion is from the water right here, as you see. So doing so will produce Hb plus, the conjugate acid of that base, and then of course the conjugate base of the acid, the original acid here. So the water is not going to be a part of the equilibrium because water is a pure liquid. You do want to make sure you include that in the base reaction. Now, weak bases only partially ionize. Very little of it ionizes, less than 5%. So then you just go ahead and work out your ice table to figure out what is present at equilibrium. You fit it into your Kb of that base, so you look up the Kb value, and you'll notice that the concentration of the original concentration of the base is so much greater than that of the amount that ionized, because there's more of the base than the ions that make up the base, as you see here. So with that, you can zero out your X and solve for your concentrations at equilibrium. You once again have to validate using the percent ionization. Let's go ahead and look at FRQ, or I would like for you to try out FRQ number 1, okay, for homework tonight. Given your understanding of what a weak acid does, what a weak base does, depending on what the scenario is, whether it's an acid or base scenario. So we know that when you take Ka times Kb, we know this very equation, you get Kw, which is water's equilibrium constant. And this is actually, I'm going to show you today how that this equation links to truly the equation that makes up the acid and its conjugate base. It has to be its conjugate base that's related to that, okay? So we know this is your acid right here, and this is the conjugate base of that acid. And when I take the acid and I ionize it, like I see here, into its parts, the two ions that make up that acid, the hydrogen ion and the conjugate base of that acid, what happens is you have this weak acid in equilibrium, and thus you can write a Ka reaction for this. Now, why this is a Ka is because of the presence of this hydrogen ion right here. So this makes this reaction a Ka reaction. It's an acid ionizing, and thus the A in Ka stands for the acid equilibrium constant, which is this acid equilibrium reaction. It's products over reactants, so I'm going to take the products as we usually do over the reactants for the equilibrium expression here. Now if I take the conjugate base of that acid and I do a hydrolysis, so it's ionizing also in water, I know that a base likes to accept a hydrogen, and so I need the water there. And as a base accepting a hydrogen, I'm going to show that with the arrow and the proton. transferring over, we now have a substance, we have the acid, the conjugate acid of that base that we see in this reaction. So this is the conjugate acid of this weak base. And of course, we have hydroxide ion being produced out of that reaction. Thus, we have a Kb reaction as well as expression. And by the way, I do want to show you that yes, the hydrogen ion also we can go reverse and see the hydrogen ion go, or the reaction go reverse in that way. And the proton transferring between the acid and the hydroxide ion. Now, so when we take the acid and its conjugate base, and we see the acid ionizing in water and its conjugate base ionizing in water as well, we then can take the Ka and Kb, and we're going to add up these two equations. Now, we remember that when we add up these two equations, what we do to the K values is multiply that. And that's what I'm going to show down here. I'm going to add up these two equations, and then I'm going to see the how the K value and expressions work out. So adding these two equations, the conjugate base, or the bases, cancel out. The acid also cancels out. And notice that we are left with the water's ionization, water's self-ionization. So this is called water's self-ionization. Now let's go ahead and see what the expression gives us. So multiplying these two expressions, and that's what I've done. I've multiplied all the numerators and then multiplied the denominators. This is what I get. I notice that some things can cancel out. The same things that cancel out in adding them, adding the equations, I'm also canceling out when I see the K, when I multiply the Ka. So I'm left with exactly what I would expect, which is the equilibrium, water's equilibrium expression, which products and of course over reactants. But the reactant is a liquid, pure liquid, so we won't include that in the Kw expression. And we call this Kw. And that equals a constant that we found experimentally at 25 degrees Celsius to be 1 times 10 to the negative 14. Now, when we take the negative log of this, so I'm trying to achieve the pH as well as the POH. There's a function in logarithms where if you're multiplying, if I'm logging something that is the product of two factors, what I could do is I can split each factor up and add them together. And that's what I'm doing, splitting them up and adding together, which yields pH. When I split this up, this is pH. And then, of course, when I split this up, negative log of OH is POH. I add them up, and now let's look over here. And I would do the same thing over here with the 1 times the constant, the Kw constant. And I know the negative log of 1, if you put it in your calculator, is 0. So this, I can say for sure, is 0. But I also know that the negative log of 10 to the negative 10, or negative 14, is 14. So I'm deriving for you all how this equation, pH plus POH equals 14, comes about. It actually is water's self-ionization. And we can do the same here with the Ka and K. Since I'm multiplying these two, this is Ka times Kb, and that equals water's, the Kw. And I can also find that pKa plus pKb equals 14. So these equations, all are equations you'll be utilizing through the whole unit. And understanding that if I have my acid and its base and its conjugate base, I see that this relationship really holds true. Ka and the Kb of that acid and its conjugate base is going to multiply to equal Kw. And that is a constant. So you can always find the Ka or the Kb of the same acid or its conjugate base. Okay, let's talk about acidic hydrogens. Acidic hydrogens are hydrogens attached directly to a very electronegative atom, usually oxygen. And that means they usually are not attached to the central atom. In other words, it's attached to the bonded atoms. So the acidic hydrogens is another attachment beyond the bonded atoms. So let's draw some and we'll see how this acid is acidic. Let's identify the least electronegative element, which is carbon. And so carbon-carbon is going to be the backbone, both carbons. And I'm going to start drawing the dots for carbon, 4 valence electrons and 4 valence electrons. And then I'm going to draw the oxygens, and I'm going to really spread them out. And to give myself a little bit of room, I'm going to make sure I put this oxygen on the bottom. And I'm going to put the hydrogen right over here. So I kind of have a mental image of where atoms are positioned and where I would put each of my valence electrons of each of my atoms. So I bond here, bond here, bond here, 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 and then I see a double bond here. So this is vinegar, by the way, acetic acid. And if you notice, the acidic hydrogens are always, like we said, on a very electronegative atom. Why? Because the dipoles are pulling those electrons. That electronegative atom is pulling the electrons towards its nucleus more so, causing this electron right here from hydrogen being removed altogether. And so when that happens, hydrogen is an ion, a proton. It's H plus ion. So this is your acidic hydrogen when you remove it. Now you're going, what about these? Well, these 3 hydrogens, this carbon isn't very electronegative. So it can't pull hydrogen's electron away from its nuclei. All 3 of these cannot pull, carbon cannot pull all 3 of these electrons that belong to hydrogen away from its nuclei, so they're not acidic. And so it really does make sense that acidic hydrogens are on electronegative atoms. Now, because there's only one acidic hydrogen, we call this a monoprotic acid. Mono means one. One protic means proton. And here is your proton right here. Why don't you draw the next 2 examples, sulfuric acid as well as formic acid, and figure out what type of protic acid it is. Now, after mono comes diprotic, and then after di comes triprotic. And really that's all that you will see beyond that, or nothing beyond triprotic. So mono is 1, di is 2, and then tri is 3. Pause and draw this out, and then you should see the answers subsequently afterwards. Alright, I took the liberty to draw both, and hopefully you can check your work from here. You will see this is diprotic because there's 2 acidic hydrogens, whereas this one, formic acid, has only 1 acidic hydrogen. The other hydrogen has to be attached to the central atom, so it's not going to have an ionizable proton here. Go ahead and look at this next one. We're looking at polyprotic. So poly means many, many protons. So how many acidic hydrogens? Draw the Lewis structures and circle any acidic hydrogens. Go ahead and draw each of these, and then make sure you draw the acidic hydrogens. Now, what you're seeing here is phosphoric acid having 1 hydrogen removed, and so this is dihydrogen phosphate. And then this is hydrogen phosphate purely after another hydrogen has been removed from this polyprotic acid. So you can see really you are to expect this to be a triprotic acid. this to be a diprotic, and then this is monoprotic here. So it really shows you the progression of what is called deprotonation as electrons are being moved, or as protons are being removed. Now I didn't give you that much space, but hopefully I edited to give you a little bit more space. I'll really make it tiny. So pause and make sure you draw this correctly. But to draw this is starting with phosphorus, and then I know there's going to be 4 oxygens, and I know there's going to be 3 acidic hydrogens, and so I'm going to just add them at the end here. Okay, so make your attachments. And this looks like a dot, so I'm going to erase this and make it the word try a little clearer. T-R-I. Okay. It looks like I'm missing an electron here. Put back my electrons. Draw my single bonds first. That's the first thing I want to do. Forgot an electron on hydrogen here as well, so I'm going to bond that. Okay, so now we see an electron right here, an electron right here. So I'm going to do a double bond between these two. I should have put my acidic hydrogen down here instead, and then I could see the double bond occurring. Maybe I'll do that instead. I'll erase this. And then I'm going to put my acidic hydrogen down here instead, and they will bond together. And here, this electron right here is going to be where the double bond occurs right here. So there's 2 bonds occurring. Okay. All right, so this is acidic here, and acidic here. So all those 3 acidic hydrogens right there. Pause the video and do dihydrogen phosphate as well as hydrogen phosphate. When you unpause, you'll see the final answer. All I did when I drew the dihydrogen phosphate as well as the hydrogen phosphate is I redrew exactly what I saw here, and then I just pulled a hydrogen off at a time. And I moved from left to right. I pulled off this hydrogen, this proton ion, or this proton first, and then I removed the second and then the third. So I didn't do much to redraw it as I originally drew. Once you have the original template, you can easily remove a hydrogen ion at a time. It says, which acid is the most acidic? The most acidic one will be the one that you removed a proton from the neutral, because it gets more difficult once you gain the ion becomes a negative to try to get rid of a hydrogen ion, which is positive. So it's harder and harder to remove a positive charged species from a more negative overall ion. So that's why removing it from a neutral substance like this is going to be much easier, and that's why it's more acidic. The removal being easier means more acidic. We can quantify exactly how acidic the phosphoric acid and its 3 different deprotonation, which is the removal of a proton from each of its from each of the steps as we remove each hydrogen ion. So here's phosphoric acid. It's a weak acid, so there's an equilibrium with the ions that make up the acid, including the hydrogen ion and, of course, its conjugate base here. So it being the phosphoric acid's conjugate base. Now we see the dihydrogen phosphate, and we're going to ionize that again. So this is the second deprotonation. Here's the first deprotonation, second deprotonation. Then we take the hydrogen phosphate and deprotonate, remove a hydrogen here, and this is the third deprotonation. So notice how we can actually look at the Ka values for each of these, and we can see, knowing that Ka, as always, is a ratio, one way or another, products over reactants. So the Ka is higher for the first deprotonation than the second one, which is higher than the second, then which is higher than the third. So each deprotonation, you're weakening the acid strength of the substance that has been that has formed, or the conjugate acid of that original or the previous acid that you see in the deprotonation process. So this acid is going to be weaker than this original acid. This acid is going to be weaker than the previous. So we see it in the value. The value is decreasing as you go from one deprotonation to the next. Thus, there's less products. And one of the products is hydrogen ion, which means there's less hydrogen ions from each deprotonation. And again, conceptually, it's the idea that it's harder to remove a hydrogen ion the more negative it gets. So this is going to be harder because there's more negative. And hydrogen ion's positive, remember. So it really does want to more likely cling to that, the original, the original acid. So we can actually add up all these equations as usual, which, by the way, means we're going to be multiplying all of these K values when we add up the equation. And we can see the overall K of this reaction, which is, in essence, a very weak acid. Still very weak acid, because look at the K value. It's very, very low. Less products for sure than reactants. What I'd like you to do is work through FRQ number 2 with those concepts and calculations in mind. If you have to do calculations, I'm sure it's just conceptual because there's no numerical values, quantitative values here. So I want to know, if I add a salt to water, whether that salt will create an acidic solution or a basic solution. Some salts are actually neutral as well, so we can add that into the mix, but really we're looking at the acidity and basicity of certain salts. And we're going to understand why one particular ion of that salt is going to either be acidic or basic or create a neutral solution. Alright, in this first example, here's your salt, Ba, and it ionizes into two parts, the cation and the anion of that salt. We're going to look to see what the cation does in water and versus the anion in water. Now, if the cation produces a strong base, you're going to see that strong base still, and strong means it ionizes completely, so it's going to BOH is going to ionize into B plus and OH minus, giving us a net equation that looks like this, which is just pure water. In other words, that ion has no significant changes in the pH of the solution, so it's a neutral cation. If your anion goes into water and hydrolyzes in water and forms a strong acid, once again this strong acid is going to ionize completely into H plus and A minus, and you'll notice when we do the net it's going to lead to water again. So it's in the creation of a strong base or a strong acid that causes the net reaction to overall be water. In other words, neutral. So we're going to see that in each of this particular example. Okay. So first thing I'm going to do is I'm going to dissociate this into the two ions that make up this salt. Na plus, and nitrate ion. These are the two ions that make that salt up, because that's what this salt is going to do. It's going to dissociate into those two ions in water. And then we're going to take each one and we're going to add it, or we're going to see how it reacts with the water. And I'm going to write water as HOH. When you react each of them in water, this one produces, now just think of water as two ions. Water has the following two ions, H plus and OH minus. So think of it that way. So who would most likely attach to the Na plus? Of course, the OH minus. And so that's what I'm going to do. I'm going to attach Na plus with OH minus to make sodium hydroxide, leaving me with H plus kicked out here by itself. Now, I'm going to do the same thing here, and I'm going to form the OH, or the nitrate, is a negative ion, so it's going to attach to the hydrogen ion. So it's going to make nitric acid, which is HNO3, and then the OH minus is what's left out. Now I have to figure out whether this substance right here is strong or weak, NaOH. And I know in my memory bank that anything with hydroxide ion and an alkali metals and alkaline earth metals with hydroxide ions are strong bases. So this is a strong base, which means it doesn't stay together. It actually is going to ionize into two ions. And the two ions are Na plus and OH minus. So if you think about it, Na plus is still Na plus here in the products. And so this reaction is going to lead to water. So basically, Na plus does not do anything. You're not forming anything new. It's still water ionizing, self-ionizing. Likewise. So I do want to write that down, that this is a strong base. Now this here is a strong acid. And as we know, strong acids ionize completely into the parts that make that strong acid, the hydrogen ion and the nitrate ion. Once again, the nitrate ions, if you notice, they'll cancel each other out and you're left with water self-ionizing. So these two ions are neutral ultimately in the end. And I will label them because they produce, it's just water self-ionizing. They create water with its self-ionization, which means it's neutral. And you should know that if you're producing the same amount of hydrogen ions as you are hydroxide, you are neutralizing. The reaction is being neutral or neutralized. And say moles of it too. Now we're going to see when salt produces a pH that's greater than 7. And we're going to understand why, okay? And it has much to do with the fact that you're forming a weak acid, and that weak acid is going to form a more basic solution in the end. So this is a basic salt. Once again, I'm going to take my salt and ionize it into the two ions, cation and anion. But then I'm going to see that the anion probably has some or will hydrolyze in water, so it reacts with water to produce a basic solution. And that basic solution is also, a basic solution and a weak acid. And that weak acid doesn't ionize. It doesn't ionize, so that's why the anion isn't going to isn't going to cancel out. And that's why there's a Kb for this. This is a Kb reaction. Remember that Kb can be found by taking Kw divided by Ka of that acid, okay? Let's go ahead and dissociate this into the salts that make up that salt. We're going to react each of the ions in water. And I'm going to write water, HOH. And then I know that NaOH is going to form, and that's a strong base, plus H+. And I certainly know from that since this is going to dissociate into two ions, Na plus and OH ions, the sodium is going to cancel out, leaving you with just water self-ionizing. And that is going to be a neutral ion. So this is a neutral ion. And that neutral ion is because you're creating this strong base here. Now let's look at this F minus. When F minus reacts in water, it's actually going to produce an equilibrium where you're forming HF, which is a weak acid and hydroxide ion. And that hydroxide ion is what's going to make the solution a basic solution in the end, the presence of that hydroxide ion. Now, this acid is really, hydrofluoric acid is a weak acid. So that's why we don't dissociate it completely. It's actually going to only partially ionize. And that is why this substance or this reaction holds true as is with the production of hydroxide ion. And so this solution is basic, which means the pH is going to be greater than 7. Let's look at the next example. In the next example, you're looking at how you can form an acidic solution from a salt. So we're looking at a salt that actually will be acidic. And what makes it acidic is you're actually forming a weak base in the end, okay? And we'll see how this works from the salt. The salt is Ba, and I'll always do that. I will always show the dissociation of that salt. In other words, the dissolving of that salt. So when ammonium chloride solid dissolves, it dissolves into these two ions. I'm going to do the chloride ion first, okay? When the chloride ion reacts with water, HOH, you're going to see it form hydrochloric acid. And hydrochloric acid is a strong acid. And we know that strong acids are going to dissociate or ionize completely into, and by the way, I'm going to write neutral since I have my black marker on, or my black pen on, but it's going to dissociate into two ions, H plus and Cl minus. And you'll notice that Cl minus just cancels itself out between the two sides of the reaction, leaving us with water self-ionization. And that's why this is a neutral solution, because it's just pure water ionizing into equal amounts of hydrogen ion and hydroxide ion. Let's look at the next example, or let's look at the cation. The cation is ammonium. When it ionizes into water, it's going to be in an equilibrium situation here, where you're forming a weak base, which is ammonia. And of course, hydronium ion, I'm going to maintain the water. Since the water is in this reaction, I'm going to maintain it by saying hydronium ion. So this hydronium ion is what causes the pH to be less than 7. So this is what makes this acidic. And the pH is going to be less than 7. And why this is the case, of course, is because you're creating a weak base. Ammonia is a weak base, and that weak base will not ionize any further. It's actually going to stay mostly NH3 molecules in the solution. It's hardly going to ionize. Please work through FRQ number 3 and check your work as you go through it. We're getting into new titration soon, so we're going to talk about equivalence point and neutralization reactions. Equivalence point is has the word equal in it, and so there is something equal, and that's the point at which the acid has been completely reacted with or been neutralized by the base. And the equation of choice looks very much like a dilution equation, which is MaVa equals MbVb. The A actually stands for the acid, so this is the molarity of the acid times the volume of the acid, and we want to try to make it equal to the molarity of the base and the volume of the base. We've always understood that molarity times volume equals moles, and so really what you're doing is making the acid equal the base at the equivalence point. Recall a little side note that molarity is moles over liters. Volume is in liters, so multiplying these two, you get your mole units. Just a little reminder because it's really important that you know this relationship. Now, of course, I like to add the stoich into this equation so I don't have to do stoichiometry. And how I add the stoich into this equation is to account for the neutralization depending on if the acid is monoprotic, diprotic, or triprotic, or if the base is monobasic, dibasic, or tribasic. To account for the stoichiometry in the reaction between the acid and the base, I just add the number of protons that are, or not add, sorry, I multiply the acid side by the number of protons. I multiply the base side with the number of hydroxide ions that base can contribute. 1 mole of that base can contribute. So the hydrogen ion and the hydroxide ion numbers are really added to account for the stoichiometry between the reactants during the neutralization reactions. So what is a neutralization reaction? In origin, this reaction is really a double replacement reaction, and it's between an acid and a base forming a salt and water. We'll see it down below as an example. As long as either the acid or the base is strong, these reactions go to completion until the limiting reactant is completely used up. So as long as there's one of them that's strong, acid or the base, you're going to see them as a one-directional reaction that is neutral, limiting, with something limiting, one reactant limiting and the other reactant excess. We prefer to write these reactions in their net ionic form, where spectator ions are eliminated altogether. So let's go ahead and review this. Here's our acid. Here's our base. This is a strong acid. Mind you, this is a strong base. When I react these two, I am going to form my salt right here, but the salt is not solid. It's aqueous because we're in solution. So it's a soluble salt, by the way. And then you're going to form water. So here's your salt, here's your water. So this is called the balance overall reaction. Of course, there's a little error, mistake here. You can ignore that. The first step is to ionize what can be ionized. And anything that's aqueous you can dissociate into ions. And that's why I've dissociated hydrochloric acid into its ions. Sodium hydroxide into its ions. Sodium chloride into its ions. But I did not dissociate water because it's a liquid. It's actually my driving force. You'll notice that my spectator ions, when I cross them out and aim for my net ionic equation, so I'm going to cross out all my spectator ions, I am left with water, the driving force, and the ions that make up water, which is hydrogen ion and hydroxide ion. So we're titrating. The whole idea behind understanding this is to do this titration. So oftentimes you have an unknown acid. So the scenario is you have an unknown concentration of acid. And you measure out a certain volume of it. So you actually do know the volume. So you measured this part. And that's what's in here. And then you get to the base. In here, in your burette, this is called a burette, is your base. So you have a known concentration of your base. And of course, this burette is special because it actually measures precise volumes. So this is markings for volume, milliliters volumes. And so we can easily figure out, when we get to the equivalence point, we can figure out the VB of when we hit what is called the equivalence point, or really the end point. And I'll delineate those two words, end point and equivalence point. So you're adding base to this acid and they're reacting until you reach a certain point called the end point. And it's color change. That's how we know that we've reached the equivalence point, is because the end point is when the color change occurs. Okay? So this is what your titration setup looks like. It's a very general description and how simple it is for you to be able to get all your parts, MB, VB, and MA, in order to solve your problem, solve the unknown concentration of MA. That's what we're going to do for these examples. They're really easy because all we're using is this equation for the equivalence point. And given that I've given you a short little descriptor of titration, you should be able to read these problems and understand conceptually what's happening, okay? So here's my first example. My first example is number 9. And again, I'm just using the top equation, MAVA equals MBVB. And what I'm going to do when I go through this equation is I'm actually going to assign which one's which. The acid MA versus MB, or VA versus VB. So here we go. The first one says you've got an acid reacting with a base and they're both strong, and you form water and sodium sulfate. The base is 2 molar to begin with. So I know this is my MB. And it says that will be required to completely, so now I'm looking at my VB, or VA. So this is the volume of my acid. And this here is my concentration of my acid. Very easy equation, but note, this is a diprotic acid and this is a monobasic base, okay? So my equation is going to look like this for this problem. MA VA times it by 2, because it's diprotic, equals, I won't color coordinate all the problems because it takes a little time, MB VB times 1, because it's monobasic. So for the acid side, Mrs. No decided to multiply, because I have 2 hydrogen ions in 1 mole of the sulfuric acid, I'm going to multiply that by 2. And then for the base side, I'm only multiplying it by 1 because it's monobasic. It's only contributing 1 hydroxide ion. So I substitute everything in except for what I'm trying to find, which is the volume of the base. So VB is what I'm trying to find. And in doing that, I should get my final answer. 2 times the MA, which is 0.500, times the volume, which is 75.0 milliliters. I'm not going to put units in here. Equals, and I'm going to do that in blue for this particular problem. The MA is 2.00 times VB and times 1, which we know is the same number. So you're solving for VB, and you should end up with 37.5 milliliters of sodium hydroxide. I really do feel like these problems are quite easy and straightforward, so I'd like you to pause and make sure you work through these 3 problems on your own. When you unpause, you will see the final answers and the work for all of them. All right, so here's the answer. And check your work, please. You'll note that this is a diprotic acid, 2 here, dibasic salt here, or dibasic base, so that's why the 2 is here. Also for number 13, same thing. You have to make sure you see this triprotic acid right here, okay? And this is monobasic, so you don't really have to multiply the 1 out over on the side. Again, this accounts for the stoichiometry. If you were to write an equation, you'll see a ratio between the potassium hydroxide and the phosphoric acid would be 3 to 1. So that's why you're seeing that 3 multiplied on the acid side. All right, let's go ahead and go into pH curves. So when you do a titration, and we're going to do a full-blown titration on paper, you see that, and we're going to draw a pH curve, you'll see a pH curve that comes out of this titration. And oftentimes the pH curve, it's exponential, and that's why you're seeing this exponential relationship. A couple of notable points would be the equivalence point. The equivalence point is actually the exact point which we call in math inflection point. It's when the concave up versus concave down, the concavity changes. So that's what we call the inflection point, equivalence point. The equivalence point is where there's a rapid pH change. Notice how there's this really sharp vertical line here, and that sharp vertical line shows that there's a sharp change in pH. And that occurs, and when that occurs, we also know that at that point, the hydroxide ion is equal to the hydronium ions. So that is the equivalence of what we're seeing for what is called the equivalence point. So that's what's equal. Now before that, you're actually going to see hydronium ion. It's acidic, so hydronium ion is going to be greater than hydroxide ion. Now it's basic up here, that means there's more hydroxide ion than hydronium ion. So the logic really prevails as to what you're seeing in this curve in terms of the 2 ends here versus the inflection point, which is where the equivalence point is. So know this very basic idea of this curve. And all we're doing really is adding the base slowly to the acid when we're titrating. And that's why it's getting more, it's getting more basic as time goes by. So its pH is going up. Buffer solutions is what makes this unit more challenging, or the most challenging. Buffers are, it's a simple definition. It's any solution that has the ability to resist changes in pH upon the addition of small amounts of acids or base in an equilibrium reaction. So this must be in. Therefore, buffer solutions have components of the following. Usually a weak acid or a weak base, and thus there's this equilibrium reaction. And its conjugate base or conjugate acid. So let's talk about how a buffer works. For something like a weak acid and a salt of its conjugate base, that means the salt has the conjugate base of the weak acid. This is a type, you can make a buffer like this. What happens is when there's more hydroxide ions added, so when there's more base added, you'll find that the acid will react with the base. So that's why the acid component, the weak acid. So I'm going to write the word the weak acid is going to react with that. Now, when you add hydrogen ions, how the buffer solution is going to buffer and prevent changes in pH is the conjugate base is going to react with the hydrogen ions that are added. So the conjugate base of the weak acid. And of course, you've had a lot of practice with the BL model, the Bronsted-Lowry model of what is defining an acid and a base versus its conjugate. So let me kind of use an example of this, okay? I'm going to make up a weak acid like HF, a real example. And then I'm going to add NaF. So now notice, HF is the weak acid, and F minus specifically, not the Na plus. We know that's a neutral ion. The F minus is going to be the conjugate base of that weak acid. So that's how we're going to go about making our buffer solution. So I add a little bit of hydrochloric acid, and then I add some sodium fluoride salts, pellets, solid salt pellets into that solution, and now I've made a buffer solution. That's how easy it is to make that buffer solution. So there are several ways to make a buffer solution. There's actually 5. You can simply take the weak acid, which we did here, and then just add some salt of the weak acid with its that has the conjugate base. So that's what it means by salt of the weak acid. So really it's the conjugate base that you're adding, which is F minus, conjugate base of the weak acid. You can also add a weak base and the salt of the conjugate or of the weak base, which means it's the conjugate acid. An example of that would be something like NH3, which is a weak base, and then adding the conjugate acid, which is NH4 plus, but a salt. So I'm going to make, instead of a plus, I'm going to erase that plus, and now I'm going to make a salt. And that's how NH4 ammonium is. It's usually carried as a salt, ionic salt of some sort that I can purchase out in the stores. Now there's another 2 ways. These 2 ways are the difficult ways. It's during titrations that this happens. What happens during a titration is sometimes you'll form what is called what's present at equilibrium in that reaction is a weak acid and its conjugate base. And usually that happens when you're adding enough of a base, a strong base, to the weak acid while you're titrating it before the equivalence point. You'll know when we do a full titration how this works. And then the next example is a weak base, and of course the same. Opposite is true. If you're adding a strong acid, titrating a strong acid with the weak base, it's right before the equivalence point that you'll see the weak base and its conjugate acid present. And the 5th way is one of the simplest ways, which is just adding a weak acid with a weak base together, and now you have a buffer solution from that. So this is the 5 ways to create a buffer solution. When there's a buffer solution, we use an equation called the Henderson-Hasselbalch equation. It's kind of a mouthful, so we're going to say HH equation, okay? You use this equation to find the pH of that buffer solution so that you can figure out the amount of acid and its conjugate base, or base and its conjugate acid present in a buffer solution. The equation's origin actually comes from the Ka or Kb expression. So I'm actually going to derive this so that you can know that you can use the Ka or the Kb to solve for any problem. But I'd like you to also know that it comes from, or you could use this equation, and I plan to use this equation because it's much easier than using Ka and Kb. And that's because you have to actually dilute your concentrations, and that extra dilution makes the Ka and Kb a little bit more difficult to address or to use than the Henderson-Hasselbalch equation. There's no dilution. You can actually go straight to the moles to figure that out. So this equation is for a buffer solution. So anytime you hear the buffer, that means you're going to go to the HH equation. So how do we go about taking the Ka expression and getting the Henderson-Hasselbalch equation? How do we derive the Henderson-Hasselbalch equation from this Ka expression? We're going to focus on the H plus concentration. So I'm going to circle that. I'm going to solve for H plus. When I solve for H plus, I get the Ka times the HA concentration over the A minus concentration. Now and then what I'm going to do is I'm going to take the log of that. So negative log, sorry. So I'm going to take the negative log here, and I'm also going to take the negative log over here on this side as well. In doing so, now I have the definition of pH. That's why I took the negative log. So pH is negative log of H plus concentration, and so as I define that, I get pH on this side. Now, I'm going to use a property of log, where if you have log of x times y, you split up that xy by logging each one, and you're adding up each of those logs. So this is a log identity. In doing that, I'm going to split up the Ka from this ratio here. So I'm going to split Ka, when it's multiplied times this ratio, I'm going to split it up and add them up together. So essentially I have negative log of my Ka, and then I also have negative log of my HA, and out of room, so I'm going to slant this a little, over A minus. Now, P, again, we see pKa defined here. So negative log of anything is P of something, and then Ka. So it's pKa. So I'll write it as pKa, or pH equals pKa. And then what I'm going to do is I'm going to use another identity of log, which is if I have a negative here in front, as I do right here, I can bring the negative into my log function, and what happens is it takes the reciprocal of that. So I'm going to do just that and bring the negative in. Upon bringing the negative in, I get log of concentration of A minus over HA. So it's in fact this ratio between the conjugate base and the weak acid, so its conjugate base and the weak acid, is going to allow us to keep it in moles, because all it is taking molarity divided by molarity, which both have the same volume because they're both in the same solution. And so that's why you can keep these two values in moles as well, or you can convert it to molarity. But if you use this equation, you're going to have to convert it into all molarity, because the liters, there's liters, 2 liter units up here multiplied, and then there's a liter unit, there's another liter unit down here, so you're going to have to do your dilution irregardless if you're using the Ka expression. But notice how the Henderson-Hasselbalch equation comes from the Ka. What I'd like you to do is the same thing and derive the POH equation, solving for OH in the same manner, and that will give you the Henderson-Hasselbalch equation with POH involved in it. And of course pKb, and you'll deal with your ratio is probably going to be the conjugate acid over the weak base. So go ahead and derive it in the same way that I derived it over here. I want you to try to derive it in the same manner. Here are the properties, the log properties that I used. Please use those as well.